So far, we have learned that neither a decrease in the energy of the system nor an increase in the disorder of the system is by itself sufficient to explain the direction of spontaneous change. It is, however, worthwhile to note that all spontaneous processes which result in increasing order in the system happen to be exothermic. For instance, think about crystallization or condensation processes. A process that is exothermic transfers heat from the system to the surrounding, hence leads to an increase in the disorder of the surrounding. So one might conclude that processes that are spontaneous tend to be associated with either an increase in the disorder of the system or an increase in the disorder of the surroundings. Indeed, a full examination of all spontaneous processes suggests that the apparent driving force for spontaneous change is the tendency for the universe's energy and/or matter to disperse. Mixing of gases, dissolution of a solute in a solvent, expansion of a gas are easily recognizable examples of dispersal of matter that you have many times encountered. The figure on the right, for instance, makes it clear that gas molecules do not clump together in one part of the container, but spontaneously scatter throughout the entire volume of the container, hence spontaneously adopt a more disordered state. A clarification of the word dispersal of energy may be necessary. It means, of course, that heat flows spontaneously from a hot region to a cold region, as shown on the figure on the left-hand side. However, dispersal of energy also refers to the fact that it is much more likely for the molecules of gas to travel at different speeds than for all the molecules to adopt the same speed. These words furthermore refer to the fact that as the temperature, hence the thermal energy, increases, chemical bonds may be found in a larger number of rotational and vibrational energy levels. Hence, matter can be disordered in space, and particles of matter will populate as many energy levels as is afforded to them by their thermal energy, in a manner that is consistent with the Boltzmann distribution. So we conclude that the apparent driving force for spontaneous change is the tendency for the universe, energy, and matter to disperse. To measure the disorderly dispersal of energy and matter, we define a new thermodynamic function called the entropy, and denoted by the symbol S. The first law claimed that the change in the energy of the system is equal to the work and the heat exchange between the system and the surroundings. Since work and heat could only be exchanged between system and surroundings, any energy lost by the system was gained by the surroundings, and vice versa. In other words, the first law stated that the energy of the universe is constant. Alternatively, one could say energy cannot be created nor destroyed. The second law now claims that the entropy of the universe increases during a spontaneous process. Mathematically, the second law is stated as: for spontaneous processes, delta S of the universe is positive, which is the same as saying the entropy of the universe increases, or delta S plus delta S surroundings is positive. Let us summarize the approach we will take when assessing the spontaneity of a process. First, we will calculate delta S, the change in entropy for the system for that process. Second, we will calculate delta S surroundings, the change in entropy for the surroundings. Third, we will add delta S to delta S surroundings to obtain delta S universe. Finally, we will check the sign obtained for delta S universe. If delta S universe is strictly positive, then the process is spontaneous. If delta S universe is strictly negative, then the process is not spontaneous. Finally, if delta S is equal to 0, then the process has either reached equilibrium or the process is operating under reversible conditions.